Zeigermann. I'm from Hamburg, Germany. And on Twitter, I'm DJ Korthose. So you want to follow me on Twitter, DJ Korthose. The slides for this talk, you find them under this link, but I will share the link at the end of the talk as well. Good. So let's kick this off. So who of you likes to play chess? Who's good at chess? Few people. I totally suck, so no worries. So I'm really bad at it. But that's not the topic of the talk. So a lot of people got really excited when they saw games that AlphaZero played against Stockfish. And you will learn more about these two chess engines. And one position that was very exciting for a lot of people is, in this case, AlphaZero plays black. And this is Stockfish. And this is, well, it looks a little bit better for white. If you just look at it, black is a little bit crumbled there, and then it's pressed into the corner. And this is how the game evolved. And a lot of people got really excited because they saw white didn't evolve at all, or almost didn't move very much, while black was very good at finding this very strong position and eventually defeating white. So AlphaZero actually won this game against Stockfish. And this is very strange because the whole time Stockfish thought it was in the lead, and still in this position here, thought it was very strong, even though obviously, even for someone like me who doesn't know chess very well, black was leading. Good. So how does this work? So why does Stockfish play very differently than AlphaZero? So Stockfish is a classic chess engine. So who has played against Stockfish? Anyone who knows Stockfish? Its name. Okay, few. It doesn't matter much. So you could replace it with almost all traditional chess engine, including Deep Blue that defeated Kasparov. They all had the same, basically the same strategies. And the question always is, which is the next move that I'm going to play? You have to find out which move is the best and then choose this one. So you could ask, and I did this as well, why not just look at the position and say, okay, is this a good position or not? If it's the best position, then we will just take this. And this is what Stockfish does. It does more, but we will come to that. So there's an evaluation function. Looking at a certain position, it tells you, is this a good position or not? And those are handcrafted features. That means the programmer did that. And it only works on resolved positions. That means there's no captures or checks going on. And if it's not resolved, it searches a little bit ahead to get to a position where everything is resolved. So how does it do it? Depending on which part of the game you're in, mid-game or in-game, you get certain points for material. You get certain evaluation if something is trapped. So can you move a piece or not? Can you use it? Pawn structure, like are the pawns actually good in position? Are they attacked? How do they look like? Is your king safe? Do you have outposts like pieces that are not protected by other pieces? And then there's a lot of other stuff that will make total sense, but this is handcrafted. So someone thought about it and said, this sounds like a good idea, and this evolved over time. That's what Stockfish does. And the question is this good enough? Is it good enough to just look at a position and say, okay, this position looks good, let's take this? And probably not. So consider this position. So I'm bad at chess, but white is to move. This is the white pieces. This is structure. Obviously, it's set up by me to be like this. Well, not by me, by someone else. So what could white do? One move could be just to move. Sorry. To move. Okay. Moving this. In German, we call it Turm, then it's a rook in English. We can move it down here, just one position. And then
if you looked at this position and did the scoring of this position, it's still good because you didn't lose anything, you didn't get better, but you also didn't get worse. But then in the next move, if you did this, the queen moves from here to there, and you're checkmate. But you saved the rook. So that even though that position looked good, the next position looked extremely bad. So that means just looking at one position is not enough. You need to look ahead. So what else could you do? Who's good at chess? What would you do? Anyone? Yes? Yes, exactly. So you play this. How do you know? Is that classic position? Or are you just good at chess? You're just good, okay. I get it. So that's really good. The local evaluation is really bad because you will know, okay, what happens next? Queen has to take rook, very bad, but at the same time, that's stalemate because you can't move your king anymore. And then that's at least pretty good. So the point here is you need to look ahead. And the further you can look ahead, the better it is. Okay. And then people ask me, so if that's the case, can we not just pre-compute all the perfect moves and then store that in a table? You think that's doable? Who think that we can do that? Okay, none of you. And you can't, obviously. So going through the complete search tree of a game, like expanding all possible positions, is in this order. For tic-tac-toe, feasible, I would say. Connect 4 is 4 gewinnt. That's a pretty large number. Chess, that's a really large number. Backgammon, yeah. Go, really big. And to give you a comparison here is, that's the number of atoms in my body. Well, maybe I have a few more. But anyway, really bad joke, sorry for that. Atoms in the Earth, and then Milky Way. And then even if we took all of the atoms in the whole universe, not so good, right? So this probably won't work. Maybe we don't have to store all the moves, but we would have to go through all the moves to find the perfect moves. So not feasible, sorry. What can we do instead? So ideas. We can't do that. What would you do? So you can't like go through the whole search tree. What would you do? What do you typically do? Yes, just a few steps, and that would mean limit the depth of the search tree. Right. What else? Yes? I think you want to say something, right? Yes? No? Yeah, so you would prune the whole search tree, and you could also say you limit in breadth. So you don't do all the breadth of the search tree, but you just expand a few moves. So what's typically being done classically is in a two-player game, you view the game as one player tries to maximize. That means a very positive outcome, and the other player tries to minimize. You restrict the search depth, and this is how it could look like. And this graphic is going to be a little bit overwhelming. So I will moderate it a little bit. It's called Minimax, the classic algorithm that we're looking at. And we're looking at 4 half moves. So we are restricting the search tree in depth, not in breadth, first of all. And one of the players tries to maximize, and this is the computer player in this case, and one tries to minimize. And the computer player will be circles, but don't look at it too closely because it's a complete thing. So, first of all, we're in this position. It's the computer player's move. That's the maximizer. And what we do, we expand 4 steps ahead because we just decided. That's how far we are looking ahead. And instead of scoring each of these positions directly, we start from down here. So we will say we will start here. We use the evaluation function that I showed you before. And this says this is 10, this is positive for me, and this is even more positive. Plus infinity means we will win in this case. So, but since in the move before that, it was the minimizer, maybe the human player playing, so the human player will always choose the smaller one because it tries to minimize. So we will know if everyone plays perfectly, and the evaluation function is really good. the minimizer will choose this and not this, which makes sense, right? I mean, you will choose this. So that means the value of this one is not the value that you will use using the evaluation function, but the value that you propagate from down here. Same here. That's, again, the maximizer, the computer, and it can choose between 10 or 5, and it will choose 10 because it tries to maximize. And then up here, again, human player can choose between 10 and minus 10. It's trying to minimize, so it will use minus 10. And then up here, it's the computer player and can choose between minus 10 and minus 7, both bad, but it will choose the minus 7. And that's the Minimax algorithm. And each of you, I guess all of you, could program this in less than a day, and it will probably, without any tweaks, defeat most of us, which is very surprising on this machine here. So, because compute power is so immensely available, even something like this will be extremely strong. Surprisingly enough. Just using the local evaluation function will be really bad. So this is good. The further you can look ahead, the more compute power you need, but it's already pretty good. So someone said we will not explore all the possible moves, and this makes a lot of sense. And what actually all the machines really do is they do alpha-beta pruning. And it's really involved to look through it. So it shows a very simple example. So let's say you are here, you're trying to choose, am I going to do this or some of these moves? And if you expand this one here to the end, you will see whatever you do, you will win in this branch anyway. You will win. This is a very extreme example, but it could be that you see that you always get a very, very good result in this branch here. So, and if you find that out, you will not expand this branch here. Because you will say, why would I? I'm good at this other branch. And this is a very extreme example. So pruning means you will cut these other possibilities here. Effectively, this means that you often can search twice as deep as without the pruning. So that's already an optimization trick. So how does it work in detail? So apart from that, Stockfish puts a lot of other heuristics into this. So first of all, it prunes other parts of the tree because it will know that's a silly move. We know no one is ever going to do this. We order the possible moves which we're going to explore first, and this is very critical because if you're expanding the bad moves first, you will not be able to prune. And if you find something that looks really good, you think, okay, this looks very promising, it can iteratively deepen the search for this special move and try to find out, is it really good? And for very bad moves, it will not go very deep in the search tree. There's an opening book being used, like perfect known opening strategies. And then once you only have 6 pieces, which is not a lot, like 3 versus 3 is not a lot. But then there's table-based endgames because you know how to play an endgame. So this is just stored. This is it, more or less. There's a lot of very efficient implementation. There's a lot of parallelization, but this is how Stockfish plays. And Stockfish used to be #1. Oh, I already told you the secret. It used to be #1 game engine for chess in the world. And all the recent versions play like this, more or less. But they're still good enough to play on superhuman level on commodity hardware. It's hard to implement something like this, but it would run on this machine, it would probably beat Kasparov. Now, there's another thing, and this is much more interesting for us machine learning people. So this is not machine learning, this is maybe, you might call it AI, but what we have now, this is really machine learning. This is AlphaZero. Who has heard of AlphaZero before? Few people, good. Who has no idea what this AlphaZero thing does? Oh, okay. So AlphaZero evolved from I think AlphaGo to AlphaGo 0 to AlphaZero, and this was the first algorithm architecture, I don't know, that defeated world-class Go players. And Go was supposed to be a game that machines can never play because it has a very high branching factor. That means from every move you can play a lot of other moves, and then there's no real rules, and it's very hard. You need to be creative. So people thought machines are never going to do this, but they did. They defeated all humans. So my drawings are notorious. So I'm trying to do as bad. Sorry, not as bad. As good as I can, but it's pretty tough for me. But I still try. So the idea always is I have a current position, and I want to determine the next move. And once that is done in gameplay, I get a new position, or the game is over. And that gives me a scoring, because I would know at the end of the game I either lost, which would be -1, there's a draw, which would be 0 in my world, or AlphaGo's world, and a 1 would mean I won. So the question is, how do I get from here to there? And you see there's a lot of room, and you see there's a lot of room over there. So this visualization, it will grow a little bit. There's a couple of ideas. And this first one, I think it's pretty obvious. We are replacing the written evaluation function with a neural network. So instead of writing down the rules, we let it learn. How? Tricky, but we will see. And the hope is that this new evaluation function will see a position. Like we saw in the initial example, where we saw like, this position really looks good, and I'll see it at a first glance, because it looks good. Can we make a machine do this as well? And the answer obviously is yes, but we will see. And convolutional neural networks are really good at this. Looking at a position, understanding, is this good or not? And as I said, our hope is that we get a more holistic view of the whole game using a neural network. So how does it look like in our image here? So this didn't change a lot, but we have a model that is a neural network. It's multi-layer, but the important part is it has 2 heads. That means 2 outputs. The input is going to be the current position, not actually like really the pixels, but rather like which piece is where. So by the way, if there are questions, please ask anytime. So, and the model, what does it do? It gives us 2 predictions. A policy prediction and a value prediction. Anyone who already saw reinforcement learning will know something about it. The rest I will explain. And we will use these. Let's see how. So we have a single network, which is also surprising, because often there are many networks, because we need one for training and one for playing, and then maybe we need 2 networks because we are trying to predict 2 different things, but we only have 1. And this is ResNet style. That means we have shortcuts in the network, and because of that we can make it really deep and really powerful. And this is not the idea of the Alpha or AlphaGo or AlphaZero people. This is an old idea. Old means a few years old, from Microsoft. As I said, input is board position, and the outputs are 2. One is the policy head, so-called, which is the move probabilities. That means which of the possible moves that I have has the most likelihood of me winning the game. Okay, that was a little bit complex, but it's actually very simple. So we will see an example and you will understand. And the second output is looking at this current position. Who's going to win? Is it a -1? That means I'm going to lose. Is it closer to 0? That means not so sure. And +1 means I'm going to win. We get these 2 outputs from the neural network. Again, example. So we are sticking in this position, and the value that we're getting from it in this example is, I think this should be -0.7. That means it's pretty likely not a good position for us. And then we get, let's say there are 3 possible next moves, and the first move get the probability of 0.3, the second one 0.1, and the third one 0.4. That means this has 30% chance of being the best next move, and then 10, that doesn't add up, right? It should. I'm sorry for that. It should add up. Let's say this is 0.6, so it should add up to 1. So we're probably going to take this one. So that's how it looks like. So this is who wins. Probably not us, but looking at this position only, but what is likely to be the best move. And we could play like this, but there's no search involved so far. And we know just by using zero look ahead, we're probably not going to be good. So we need to add something, a search. And this search is different from the first search, very different. It's called Monte Carlo Tree Search, and it doesn't limit the search tree in depth, but in breadth. So we're always going down to the end, but we are not playing all the games, just very few. No, good. Let's see how this works. So I think I corrected the number here in this drawing, forgotten the others, sorry for that. So we're pushing this evaluation through something called Monte Carlo Tree Search, as I said, and this can be viewed as a policy improvement. And I think that's also the official name. That means you get these probabilities as a prior, you push it through this, and you hopefully get better probabilities here. And let's say those are the new probabilities here, and in gameplay, you always choose the best, which makes sense. You always want to play the strongest move when you're really playing. So in this case, we would choose this position, and this tiny square is just the tiny version of this big square. I hope that makes sense. So we have pieces somewhere here, so we choose this. We either end the game with this new position, or we're starting it all over again. The tricky part is actually how this works. So otherwise, it's pretty simple. So, okay, I said this already. So we're using the original output from the model, the policy head, to kick off a simulation. So this is our prior knowledge. We think this is going to be the probabilities. Now we explore the game tree, and you will see in a second how we do this based on these priors. We come back to this, just that you know, at a certain point of this thing, we play a simulation, and we are playing a simulation again using the model probabilities. So we stick positions into the model. You will understand in the next slide, and make this very powerful. We choose a certain number of iterations, like how many games are we going to play until we make a decision. And in AlphaZero, in the original AlphaZero, it's 800, just to give you a number. So not very many. Also, as a side note, the number of position expanded in this approach is 2 orders of magnitude lower than in Stockfish. So it's not brute force, but it puts a lot of energy into deciding which are the best positions to explore. And at the end, you saw this in the visualization, you get new probabilities based on that simulation. So first of all, we need to understand what Monte Carlo experiments are. Who knows what a Monte Carlo experiment is? Sheila knows, yeah, good. So instead of calculating the real perfect number, we make random experiments and sample. So this is a very good example, the classic one. I stole this, that's why it looks good. We're trying to find out what is pi. And you see that's a moving image, so this is the number of samples, and the higher the number of samples goes, the closer we get to pi. And what do? So we randomly generate points between 0 and 1, 0, 1, and then we find out, is this within that circle here? And if it is, we count it as within, and if it's not, we count it as outside of the circle, and using this information, this ratio, we calculate pi. Obviously, we need to have a measurement of, are we outside that circle, yes or no? That's cheaper than pi itself. So we just calculating the distance from 0, 0 to the point. And if it's smaller than 1, it's within the circle, and if it's larger, it's outside the circle. And that's just a way of doing things where you can't perfectly measure something. And we're also doing this for the gameplay, but it really gets a little bit more complex. Again, something that could overwhelm you, so I will guide you through that. So in Monte Carlo Tree Search, we have 4 phases. and the first phase, we're just looking at this now, is called selection. That means, imagine that our search tree is already built up like this. And using a certain strategy, we will consider which of these moves looks most promising, or which of these moves are we going to expand next. And that's called selection. In this case, we're choosing this one. And the next phase, we expand it. That means we choose one random next move, this one. And the numbers inside these circles, they mean how many simulations have we run within that circle, and how many of them did we win. And that means for this one, we ran 3 simulations, and we won 3 of them. So this looks really promising. That's probably the reason why we chose this one to expand next. And again, in the same fashion as this Minimax thing before, the dark ones are one of the players, and the white ones are another player. That's why this says, okay, I played 6 simulations, this plus this, and I only won 1 of them, because this one won 5 of them. Yes, so basic mathematics is always a little bit hard for me. So, but we still choose this one. It's our game now, we choose this one. And now we simulate to the end. And that's important, because we don't restrict the depth, but we always simulate to the end of the game. Because often that's the only reliable information. Are we going to win from this position or not? Because we can't use all of the search tree, because it's just too big, we sample over it. That means we play out a random number of games and use the input from the model to find out which is probably the best moves that we're going to play next. And in the end, we will count, we collect, and then let's say this is going to be a win again. No, it's not a win.
It's for the other player.
Yeah, it's a win for the other player, right? Okay, so we. Right, exactly. So that means one more play. Ah, yeah, right, you're right. It is a win for us. So one more win, again lost. So this looks pretty good. So, right, those are the 4 phases, and we will repeat that all over. And I heard that Monte Carlo Tree Search has a lot of applications, so it's not invented by the AlphaGo or AlphaZero people. I think it's 10 years old, maybe 15, but not very old. But, well, one way of doing it. And now you get the element of random sampling into it. So we are no longer accurate or anything. Oh yeah, I said this before. We need to choose which of the moves to expand next, which are we going to select. And there's 2 ways that you have to balance a little bit. And you can see, like, how do you go on holiday? Do you always go to the same destination because you know that's good? Like I might do Mallorca or something, you know that's good, Mallorca, you go there. Or are you trying to explore new places you've never seen? And it might be that, I don't know, somewhere else, Cape Verde are great and I should go there and try that out. And that's the same decision that we're making here. Are we exploiting? That means, are we always going to choose moves with high average win ratios? Or are we going to explore moves which we haven't explored a lot yet? And there's a constant that you can tweak a little bit, and the paper on AlphaZero is not very accurate on how you choose this, but you could experiment with that if you implement it. Okay, so this is Monte Carlo Tree Search, and now going back 2 slides, sorry. 3 slides, 4 slides to this image again. So now gameplay is actually done. That's how gameplay works. We have all the parts in place. We use the model. We use the Monte Carlo Tree Search. We make the next best move, and then we're probably going to win, or maybe not. What's the caveat in this? I mean, is this going to work? Oh, I mean, why is there a right side there? And the better part of the talk on the right side. What is missing? Sorry? Sure. So, training of the neural network. First, it's initialized randomly, so it makes random very bad predictions, just something. You don't know. So it's not at all reliable. So if you didn't have a trained network, this wouldn't play well. It would be horrible. So you need to train it. And going forward a few slides, this brings us to the third idea. And we're going to use reinforcement learning to train that. And it's a very special style of reinforcement learning. I looked at reinforcement learning before, but this is very different, but it still could count as reinforcement learning. And it's done by making this chess engine play against itself. Like, I think it was in the 70s war games. Anyone? Yes? So the computer played against itself and it found out, okay, nuclear war is not a good thing. So we're actually doing this here. How would this look like now? So I changed my drawing a little bit. So now we are in self-play mode. That means training mode. Over here, training will take place. So we're pushing over some stuff from here to there. And the model is between that, because we're using it for prediction, obviously, but we're also using it for training. And now also this changed in a more or less subtle way, because we're not always choosing the best move here, but we might sample over these possibilities. So also explore moves that don't look very promising, at least at the beginning of the game. So it changed a little bit. Reinforcement learning in a nutshell. Everyone always shows this graphic, which I also stole. You have something that's called an agent. Sometimes it's called, I think, an actor. So it's not always clear. And the important thing is it's active. It does something. It can make something. Like a chess engine, it does something, namely executing an action. And this action affects an environment, in our case, the gameplay. So you make a move, I don't know, you move a pawn, you get an effect in the environment, which would be the simulation of the chess game. It gives you an observation, that means new position, or what move did the opponent then make, and it also gives you a reward. And the reward, in this case, would be, did we win or not? Because this is our reward, it's chosen arbitrarily, because this is our reward, and we only get it at the very end of the game, that has implications on how we're going to train the model here. Okay, so we're trying to maximize the cumulative reward, and that means this holds true for all reinforcement learning. We are specialized, but this is how reinforcement learning works. More or less always. Good, we have special cases, but we will look into that. This is again overwhelming, but if you look at it for a minute, it becomes really interesting, because that's a taxonomy of reinforcement learning algorithms. This is model-free, policy optimization, and all the interesting stuff takes place here, maybe a little bit there. That means they're model-free, meaning they have no idea how the world actually works. So if you let this play a Super Mario game, it has no simulation of the game itself. It doesn't know how Super Mario really works. It just tries out things and learns from that. And on the right side, on the other side, they are called model-based reinforcement learnings. And there's this single thing here, this AlphaZero thing, in this hierarchy here, that has a given model. That means AlphaZero doesn't have to learn the rules of chess, but instead, the programmers of AlphaZero, they give it to the algorithm. That's why AlphaZero is pretty strong in chess, it's pretty strong in Go, and it's pretty strong in shogi. But arguably, it might be possible to learn the rules of the game itself, and you just get punishments if you cheat or something. But the rules have been given to AlphaZero in advance. That means it cannot make an invalid move and get a bad reward for that. Not possible. That's a design decision they put into it. Not sure why no one questions it, but maybe people do, but this is very, very unusual. So some learn the model, like the word models of, what's the name of the Schmidt-Huber, who arguably invented this. Some even learned the model of the world, but we have been given that model. Okay, interesting. So, as I said, we get the reward at the very end of the game. So there's no other way, at least in this case, to judge, did we make good moves, than to check, did we win the game or not. And because of that, we need to record the trajectory. That means all the moves that we did from the beginning to the end, because we need to score all of them. How does this look like? It gets more complex, but I think as you see this evolving, I will guide you through this. So record a trajectory here. That means this was the first position, then the next, and so on and so on. And eventually, after a certain amount of moves, someone won the game or draw. So it's finished at this position. So we record all the positions from beginning of the game to the end of the game. What we also record is the outcome. Like, how did it end? Maybe -1, maybe 1. And then we also record all the intermediate policy predictions here. Like, how did we say are the probabilities for this move, which you don't see up there? It's very hard to show it now. And how was the probability for this? And we might not even choose the best one all the time, because in training mode, we sample over that. That means with 50% chance, we take this move, 10% chance this, and 40% chance this. So we might take a bad move here, and we might still win, but it doesn't matter much, but because we are training now. So this is what we stick into the model. That means the input, this arrow here, goes into the model, and is of the same structure as this one. So, works. This model makes a prediction. It's context-free. It just looks at the position, makes a prediction, and this might be the prediction. But now we know better, because we know, did we win or not? So we can see, okay, the prediction that you're making, does it match the actual outcome of the game? And then also, it makes a prediction for the policy, but since we improved the policy here, with the Monte Carlo Tree Search, and it should be better now, we're also sticking in the improved policy and telling it, so since we improved the policy, we're pretty sure that's the better policy, and compared to this policy. So that's first step in training. That means we're using the same model, and also, surprisingly, if you do this in the self-play mode, we just have this single one model. It used to be very different in AlphaZero. We have just one model, we train it constantly, and we use the improved versions immediately after it improved. So I haven't shown how we improved it yet, or how we train it, at least not in detail. So it looks a little bit similar to supervised learning. So the training itself doesn't differ, but the way we collect the data. As you saw, we play games against ourselves, and the outcome of the training also influences how we collect next data. That's one of the ideas of reinforcement learning. I said this, model starts at random. So first, it's randomly initialized, very bad. We collect the data, like the outcomes of the games, and collect, well, once the game is finished, we collect this as a trajectory from beginning to end. Also said this, we use the model to collect new data. Now the losses are interesting. I said there's a difference between the prediction and the real outcome, and we use mean squared error for the value head, means the final outcome. And I said this also before, +1 for winning, 0 for draw, -1 for losing, and we use cross entropy for the policy head. Because now the probabilities are updated and probably better than the original prediction of the model. Good. I think this is the final view of the whole thing. So we're calculating the losses. That means the predicted one and this one. We calculate the mean squared error. We calculate cross entropy between these predicted ones and the real ones. We calculate the gradients like you would do in all neural networks. An optimizer updates the model. That means it finds out which of the parameters of the model brings down that loss. And then it tweaks them in the way that it knows, in the way that the optimizer knows. Often people use Adam, just the normal optimizer like you would use for all neural networks. And then you're done, more or less. That means you've gone full circle. You update it in the model, and then all at the same time, actually, self-play continues. This is very much simplified, because in the real world, all this runs in parallel. Many threads do self-play, many threads do the training. Actually, the trajectories are stored in a replay buffer, which can get really long, really large, like up to 500,000 of moves. And with each training step, we sample from it. We take a random set of samples. Mini batch, I think we just take 500 samples or something. Means we take 500 of these and stick them in at the same time. So I simplified it a little bit in order not to make it too complex. So let's sum that up. Continuous self-play. We are always using the current model. As I said, in AlphaGo, it was different because we were always playing with the best known model, and then we trained a new one, and then we evaluated it. Too complex, has been thrown away. Move probabilities were computed by the model and then improved by Monte Carlo Tree Search. We choose the moves by sampling over probabilities. And in the end game, we're doing it greedily. That means we're always taking the highest probability. And in real gameplay, we do this anyway. And in early stages of the game, we sample over the probabilities stochastically. That means if there's a prediction of 0.5, only in 50% we will take it. And that means in the beginning of the game, we explore even bad moves a little bit better, or moves that we think are better, because we might be wrong. Because at the beginning, our model is still pretty bad, so we're also trying moves that don't seem so good. I said this, we actually have a replay buffer. It means all the moves go in the replay buffer. It's fixed size, it's FIFO. That means if you stick in more, older ones get dropped. So 500,000, I think, is a good number of thinking of the replay buffer size. Yes, so only at the end of the game, it gets put into the replay buffer, and it has the complete outcome. That means who won. And you may understand, depending on which player is on the move now, it gets toggled to either +1 or -1 if it's not a draw, because for one outcome is good and the other outcome is bad. You have the full move history, the trajectory, which I can't pronounce. Maybe I drink some water and then I try again. And you have the predicted probabilities. I showed this in the image. And you also saw, hopefully, that this data matches what the model outputs anyway. So it has been engineered like this. And it's constantly retrained. Yes?
From what I understood, you need the end of the game
Yes.
to know who won, and also to know, like, to calculate the differences and all that to update the model.
Correct.
But then you don't really update the model within the game, but after each.
Yes. So that's totally correct. And not even that is 100% correct, because I just put it in the replay buffer, and when it is actually used for training, I don't know. Because it's trained in randomly sampled mini batches, so it might not be used at all. But this is rather unlikely. Yes, but only at the very end. True. And this is also very surprising, because that would mean, maybe going back, I mean, it's surprising that it works, because that would mean, even for the first position here, this one, it gets an evaluation if you won with that of 1. That means even though that position might be like the start position, we will still get an evaluation of 1. And even all the intermediate positions also get the evaluation of, we are going to win with this one. And only because in a lot of these, well, let's take the start position. It's always the same, but we should get a lot of evaluations of 1 and a lot of -1 and a lot of draws. So this should even out. But I'm still surprised it works. I think your question went in that direction, right? Why does it work?
Yeah, and also to understand, like, generally.
Okay, good. I'm surprised. And I'm surprised by a lot of these things that it actually works. So I have to admit that. Good. How does this perform, actually? And since we are really good at in time now, I might show you a full game, but we will see. disclaimer, this is marketing material from DeepMind. So DeepMind came up with this AlphaZero thing, and it moves really fast, and I have no idea how to stop it, so I need to talk over it, but I think you get the point. AlphaZero always is this thing down here, and the curve that gets plotted at the end always surpasses all the other levels of the other opponents after some time. That was against Stockfish, Shogi, I don't know, Elmo, but it always surpasses them. This is Go. These are the old versions of the same algorithm. It always surpasses them. But this is fishy because it's marketing material. So this is what they tell us. But I looked at it, and they didn't play this in the open. So you don't have the source, you can't reproduce that. So they just claim they did that. And they shared the moves of the games, but not how it came to it. And then people were criticizing superior hardware, that AlphaZero was using like really advanced TPUs, a lot of parallelization. There was an outdated version of Stockfish. They played against Stockfish 8, and we have Stockfish 14 now, which also doesn't sound fair. As I said, the game engine, the AlphaZero game engine, is not available anywhere. Neither the sources nor something that you can use to test that out, which I'm not a scientist, but for me, this doesn't sound good. Anyone a scientist around here, or did scientific work? Anyone? You did? Oh, what would you think of that? That sounds fishy, doesn't it? Does it? Who thinks that that's not suspicious at all? Okay, that's... Even if you think, you probably wouldn't raise your hand at this point. But also, I don't look into papers. I don't do this because I don't understand. I don't like formulas, but I did because I wanted to know how would you implement that. It has so many caveats that it's not possible to re-implement that. And a lot of subsequent papers addressed that and said, okay, we don't know how they meant it. We did our own implementation and made our own experiments because this is not in the paper for AlphaZero. So not so good, I would say, but someone implemented this in the open, Lila Chess 0. And it also works like this. I can donate some of my compute power on my maybe GPU-based system, probably not this one, and then collectively people trained the Lila Chess 0 engine, which is implemented based on the ideas that I just showed you. And they try to make it better and better and better. And last year, around that time, it absolutely sucked. It was really bad, but it got better because a lot of people donated processing power and we trained that model. Now, in April, it actually became the unofficial, because there is no official, but it became the unofficial chess champion of chess engines. And it beat Stockfish by scoring 162 of 300 points. Good point. Good point. It must be because this has been controlled by independent people. I think it must be a very recent version, but I will want to know myself. Let's see. Yeah. Oh, okay. Stockfish. Let's see if you find it. Oh no. What is this? What does it want? Anyone seeing it? Version? Stockfish? Maybe I search for version. What do you say? Version. Version? Not good. Let's see. I'm very sorry, I would like to know, but I don't know it. I'm pretty sure it must be the most recent version at this point, but I don't see it. Maybe if someone finds out, tweet it. I would also like to know. Did it say? Oh no, this is AlphaZero making headlines by beating previous versions of Stockfish. So I think it must be the most recent one, but I'm sorry, I can't answer this, even though I think it's very important. I should. Or maybe you help me with that later. So I'm not saying Stockfish is less powerful than Lila Chess Zero. I'm just saying this different approach can compete. And I think last week or the other day I read something that another competition, Stockfish won again. So I'm not saying this is the best technology you can have. And there's no way of improving it. I do say it can be of similar strength. So I looked at some of the chess matches, recent ones using Lila Chess Zero, because now you can look at all the parameters. It's all played in the open. Everyone can use the chess engine to play. And I'm not good at chess, but I understand the power of the positions that Stockfish had very, very hard time finding out that they were really powerful. So this knight here effectively controls these two rooks. They can't move anymore. We're taken out of the game. Very, very nicely protected, also by the rooks here. And what excited people who are really good at chess, not me, because I suck, is the way this game evolved, because Lila Chess Zero used the king as an active element of play. Instead of like protecting it and hiding somewhere, it did a queenside king walk. That means it moved the king up there and like integrating it into the whole gameplay, and actually defeated Stockfish doing that. And people say this was very unusual for a chess engine, especially for a very strong chess engine, and they haven't seen this before. And they were like really excited. I think chess players are also nerdy like us programmers, but you got a lot of excitement from that. So this is a different kind of gameplay, and even people say we learned a lot by watching Lila Chess Zero play against Stockfish, how we can improve our own gameplay, even very, very professional players. I have a full match, and I will just talk over it and replay it, because we do seem to have time. This never happened to me. I typically run out of time. And it's not interesting yet, but it will become interesting. Lila Chess Zero plays white, and this is all boring. Stockfish plays black. Things happen. I need to talk over it because it's boring now. So nothing too special. Still looks similar, but I can trust me on that. Lila Chess Zero playing white is trying to dominate this part of the board, and it doesn't matter much what happens on the other part of the board. You see, it gets a very strong position on the left side, but in the back of its mind, Stockfish prepares a pawn take. I know this because I watched the game. And it tries to take one of these pawns, and you see that. It tries to make up a trap, and it's very sophisticated, and now it's very close to taking this pawn. I have to pause it for a second, because, sorry, oops, did it take the pawn? I can't stop it now. Sorry. Okay, did it take the pawn already? I concentrated on the controls. Did it take the pawn on the right side? Okay, good. No, I really didn't know. So, because I think if you're good at chess, you see what Stockfish has in mind, and it tries to outsmart Lila Chess Zero by preparing this trap and taking one of these pawns. But the important part here is Lila Chess Zero doesn't care at all. It knows it will take it, but it just doesn't care. It just continues evolving this very strong, aggressive position on this side of the board. Because it knows, okay, whatever you do on that side, I see what you're doing. I let you do that. I don't mind. And then it happens as it should happen. Pawn take. Yes. So Lila Chess is one pawn ahead at this point, and it will take another pawn. It will be 2 pawns ahead, and very, very confident it's going to win, even though who's a really good chess player? Or better than bad? You're a good chess player. Would you say this position is good for black? Looking at the board? Just visually looking at it? No, right. So why can we do this? I mean, you probably, I guess you don't beat Stockfish, right? You don't. It has a limited effect and you can't move it much, yeah. So you see that, but Stockfish doesn't. But Lina sees it, and the intuition, not sure if it's true, behind that is because it looks at the board visually using a convolutional neural network, it sees that's a strong position. And it's always position over material. So leader chess 0, very strong position, it doesn't care. I think it will lose a third pawn. And Stockfish will be 3 pawns ahead at a certain point, but it will know that this is a very, very strong pawn. It can be, and there will be some brilliant moves later, which are also very surprising. This move, for example, pawn b7. You can watch how this ends. It's pretty fast, but it's just 30 seconds from now, and I'm not quite sure if it really was 3 pawns ahead. I think only 2. But you will see, I think, you will see White is going to win. At a certain point, Black will resign. But until a certain step, this handcrafted evaluation function wasn't good enough to tell that's a bad situation for us. And there are even versions of leader chess 0, I think they're called anti-Stockfish, because they look at that's cheating a little bit. They look at the evaluation function of Stockfish, and they will find out how to outsmart that. And they play very strong against Stockfish, but very badly against anything else. So just the rest is just end game. So Black will resign, trust me. So, let's see. Position for material. That should have been, now I see it, the title of the talk. Because leader 0 happily exchanges material for a very good position. And I think this one, we know the version of Stockfish. 19? No, that's not possible.
It was 10.
It was 10? Okay, thank you so much. Is it? I thought it was 14. No? Maybe I mixed it up. Okay, good. I always get confused with numbers. So wrapping it up already. So why is this interesting for a machine learning conference? Maybe I should have said it before the talk, but well, you're still here. Because it uses techniques that are well known. Reinforcement learning. We have convolutional neural network, not new. We have Monte Carlo Tree Search, also not new, and combining them in a very smart way, not relying on one of them, we could actually create, well, not me, other people could create something that's outstanding. Maybe not in the results, but in the way it plays, and then how we can learn from it. And I found this very interesting. And I told you before that for centuries, chess playing has been dominated by AlphaBeta search. And this is really old technology, and it just got better because of a little bit improvements in the algorithms, but mainly compute power. That's what I said. The new paradigm also said that we learned the evaluation function. We use Monte Carlo Tree Search instead of AlphaBeta search. And someone asked me yesterday, why not use AlphaBeta search? And there's no obvious answer to it, but a non-obvious answer that's in the paper, and the answer is this evaluation function has a very large variation in the quality of its predictions. Sometimes it's very much off. It doesn't have a good estimation. But the idea is because we are sampling over so many outcomes that this evens out, so it doesn't impact the overall result too much. But AlphaBeta search, it always propagates the best result up, and this messes with the high variation quality of the evaluation function. So they tried AlphaBeta search, but it doesn't perform well. So you actually have to have a Monte Carlo Tree Search, which is surprising, but good. And we used reinforcement learning, but in a very, very unusual way. So if you went to the introduction talk on reinforcement learning, you would have seen none of that. Or almost none of that. Oh, I'm out of time, as it seems. Perfect. And I would claim the way of playing is overall very new. It's powerful, but it's also very inspiring. And since we're out of time, maybe you have time for... We don't. So we don't have time for one question. Talk to me after the talk if you have questions or anything, the slides are down there. I will tweet that using DJ Korthose if you're interested. Yes, and I also have references to the papers if you really want to read them. I doubt that, but you can do that. So with that, thank you very much.